Let's move on to shifting the position of a force. We can apply the principle of equivalent forces and couples anytime as long as these two conditions are met. The first is that there are multiple forces acting on a rigid body, and the second is that we're not interested in the forces or stresses acting inside the body itself. Stemming from this idea is an important principle that suggests that any force can be replaced with a force of the same magnitude and direction but in a different location, plus a couple that's equal in magnitude to the force times the perpendicular offset distance. Let's see what this means using the graph shown below. The first figure shows a force F acting on the body at some distance from point A. In the second figure, we shifted the force so that it acts in a different location, which is now directly on point A. And we've added a couple as described by the principle above. If we compare figures 1 and 2, you'll notice that they are equivalent since the vector sum of the two forces acting at point A, F plus negative F, gives us 0. In the third figure, we have replaced the couple with an equivalent moment, given that the moment produced by a couple is equal to its magnitude, F, times the distance, d, between the couple. To recap the principle as applied in the graph, we see that our new force, F, in the second figure is of the same magnitude and direction as the force in the first figure, but in a different location. The added couple is this set of F and negative F, which, if multiplied by the perpendicular offset distance, can then be replaced by a moment, as shown in figure 3. Alternatively, this can be represented by the equation m equals F times d. Let's take a look at this example of a complex beam. Considering the beam shown below, find the reactions at the supports. A hint is to replace any distributed loads with the equivalent point loads. Before we begin solving any equilibrium equations, we should always break the supports up into the respective reactions. Pause here to try writing out all these reactions on your own. The support at A is a pin support, so it will carry reactions in the vertical and horizontal directions AY and AX. The roller support at C will carry a reaction in the vertical direction only, since it is free to move in the horizontal direction, giving us CY. Given the hint from above, we will replace any UDLs, or uniformly distributed loads, with its equivalent point load. There's only one UDL in this problem, which is given by Q, so we can replace Q by an equivalent force, which we will call F equiv. F equiv will be equal to the 200 pounds per feet times the distance along which the UDL acts on the beam, which is 10 feet minus 5 feet. We then get a value of 1,000 pounds for F equiv, which acts at a distance d from point A. D is equivalent to 5 feet plus 5 over 2 feet, giving us a total of 7.5 feet from A. And one last thing before solving the problem, we must establish our coordinate system. So we will select upwards as our positive y direction, right as our positive x direction, and counterclockwise as our positive moment direction. Now moving on to the equilibrium equations, we can immediately solve for the sum of Fx first, since there's only one horizontal load and one horizontal reaction. The sum of Fx equals 0 accounts for Ax acting to the right and the 500 pounds acting to the left. Our equation will then be 0 equals Ax minus 500 pounds, giving us Ax equals 500 pounds. Since there are two unknowns, Ay and Cy, in the equilibrium equation for forces in the vertical direction, we must solve for the sum of moments next to get rid of one of these unknowns. We can take the sum of moments about either points A or C, but I will choose A. Recall that forces do not produce moments about the point that they act directly upon, meaning that our sum of moments equation about A will not include Ax nor Ay. Taking the sum of moments about A, we get the sum of m about A equals 0, which is equal to 500 pounds times 4 feet. 500 pounds is positive because it will act counterclockwise in the positive moment direction, and the reason we are multiplying by 4 feet is because the equation for calculating moments involves the perpendicular distance between the point and the line of action of the force. If we extend the line of action of the 500-pound force, notice that it will meet point A at a perpendicular distance of 4 feet. Next, we're subtracting 1,000 pounds because it will act clockwise in the negative moment direction, times its normal distance to A of 7.5 feet, plus CY, since it will act counterclockwise in the positive moment direction, times its normal distance to A of 10 feet, plus 700 pounds, since it will act counterclockwise in the positive moment direction, times its normal distance to A of 13 feet. Rearranging this equation gives us a value of negative 360 pounds for CY. A negative value means that CY acts in the opposite direction of what we assumed, so CY will in fact act downwards. Finally, we can solve for the sum of Fy equals 0, which accounts for AY, the 1,000 pounds, CY, and the 700 pounds. Our equation will then be AY minus 1,000 pounds plus CY, which is negative 360 pounds plus 700 pounds. We then get a value of 660 pounds for AY. Note that instead of taking the sum of vertical forces as in the third equation, we could have taken the moments about C to solve for AY. In this second approach, we will use what we have learned in this section and replace the 500-pound force on the beam with an equivalent force and a moment along the beam axis, and then proceed as before. But first, we must break up the supports into their appropriate reactions and again set a coordinate system. I'll use the same conventions as before, so up, right, and counterclockwise will all be positive. We replace the 500-pound horizontal force 4 feet from the beam with a horizontal force at the base and a moment. The equation of a moment is given by m equals F times d, so the moment at B will equal 500 pounds times the 4 feet distance, giving us 2,000 pound-feet. From here, the steps are essentially the same as before, so I suggest pausing the video to try solving it on your own before checking the answer. Using the sum of Fx equals 0, we will get Ax equals 500 pounds. Once again, I'll take the sum of moments about point A. The equation for the sum of m about A will be slightly different. We would no longer include the 500-pound force times its normal distance from A, and instead write the moment 2,000 pound-feet in the equation, giving us 0 equals 2,000 pound-feet, which is being added since it will act in the positive counterclockwise direction, minus 1,000 pounds, since it will act in the negative clockwise direction, times its normal distance to A of 7.5 feet, plus CY, since it will act in the positive counterclockwise direction, times its normal distance to A of 10 feet, plus 700 pounds, since it will act in the positive counterclockwise direction, times its normal distance to A of 13 feet. This will still give us a value of negative 360 pounds for CY. Finally, the sum of Fy equals 0 will again give us a value of 660 pounds for AY. As you can see, shifting the position of a force will give us the same answers, so either method can be used when solving similar problems in the future. We'll end this lesson off by analyzing a real-life application of the principle of equivalent forces and couples. Let's say there's a street lamp with a uniformly distributed wind load acting on its pole. We turn this load into an equivalent point load at a distance d from the base of the lamp. Pause the video here to try and shift the position of the force on your own. To put it simply, the principle essentially states that a force can be replaced by an identical force with the same magnitude and direction in a different location, plus a moment about that new location. This moment is equal to the magnitude of the force times its perpendicular offset distance, d. So on the diagram to the right, I'll move this point load down to the base of the lamp and add a moment. This is exactly the same method we used in the second approach in the example, and you can use this method as long as there are multiple forces acting on the rigid body and the forces of interest all act externally.